empirical and molecular formulae, and examples on working out the simplest ratio of atoms and the actual chemical formula of a compound. The empirical formula of a compound gives the simplest ratio of atoms of each element in the compound. The molecular formula gives the actual number of atoms of each element. The empirical formula of a compound can be calculated from data which gives the percentage composition by mass of each element in the compound. Sample calculation. Calculate the empirical formula of a compound containing carbon, hydrogen, oxygen with the following percentages by mass. I'm given carbon and hydrogen only. So my first thing here is to calculate the percentage of oxygen in the compound. Subtracting from 100%, 40 for the carbon, 6.7 for the hydrogen gives me 53.3% for the oxygen. Calculate the number of moles of atoms of each element. I've put the equation for moles here. Moles equals mass over relative atomic mass. And then express these numbers of moles of atoms as the simplest ratio. And I find that following this format means you just don't go wrong. In this example, my mass of carbon, hydrogen, and oxygen placed in there. To get the moles, dividing by my relative atomic masses. That will give me 3.3 carbon, 6.7 hydrogen, 3.3 oxygen, and then, best thing you can do, get the simplest ratio by dividing through by the smallest. 1 to 2 to 1, CH2O. The molecular formula can be deduced from the empirical formula if the relative molecular mass is known. A value for MR can be determined using the ideal gas equation or from a mass spectrum, and I'll do separate videos on both of those in due course. But if the value for MR is given as 180, I know my empirical formula is CH2O. Let's work out the mass of the empirical formula. 12 for carbon, 2 times 1 for the hydrogens, 16 for the oxygen, comes to 30 when we add them all up. And the ratio, MR to the mass of the empirical formula is 180 to 30 is 6. Tells me the molecular formula is 6 times bigger than the empirical formula. In this case, the molecular formula is 6 times CH2O is C6H12O6. Now I know that in my example here, I'm taking my relative atomic masses as whole numbers. You may be required to do this to 2dp, as is often the case, but if you're given the atomic masses, use them as they are. Here I'm just showing this as an example of a method you may use. Next, a compound has empirical formula CH2O2. What is the percentage by mass of each element? Alright, now I'm working backwards here. Get the mass of the empirical formula. 12 for carbon, 2 times 1 for the 2 hydrogens, 2 times 16 for the oxygens, adds up to 46. Now we consider the mass in grams of each element in the empirical formula. Well, if I think of this as having 46 grams of CH2O2, I will have 12 grams of carbon, 2 grams of hydrogen, 32 grams of oxygen. Dividing through by the mass of the empirical formula, multiplying by 100% gives me the percentage of each. A compound contains 12 grams of carbon, 4 grams of hydrogen, and 14 grams of nitrogen. What is the empirical formula? I write down my masses as given in the question. Convert that to moles using the relative atomic masses in this question given. Get my simplest ratio. I'd normally divide through by the smallest, but the smallest here is 1, so that's kind of done for us. And I get my empirical formula, CH4N. The molecular mass is 60 grams. What's the molecular formula? Okay, the mass of my empirical formula, 12 for the carbon, 4 for the 4 hydrogens, 14 for the nitrogen, comes to 30. 60 for the molecular mass divided by 30. The mass of the empirical formula gives me 2. So my molecular formula will be double the empirical formula. A compound has empirical formula CH3O. What's the percentage by mass of each element? Again, get the mass of my empirical formula. 12 for carbon, 3 times 1 for the hydrogens, 16 for the oxygen, comes to 31. Now we consider the mass in grams of each element in the empirical formula. Again, thinking of 31 grams of this compound contains 12 grams of carbon, 3 grams of hydrogen, 16 grams of oxygen. I put the mass into the table. Divide the mass of each element by the total mass, the mass of the empirical formula. Multiply by 100% gives me 39%, 10%, 52%. And you'll notice those don't add up to 100%. They don't always. Apart from the fact I've taken my relative atomic masses to the nearest whole number is one thing. These are always gained from experimentation. Answers will always be approx. Bit different. Experimental data on the mass changes in combustion reactions can be used to derive an empirical formula. Combustion reactions normally concern hydrocarbons. The mass of carbon dioxide and water produced tell us how much carbon and hydrogen came from the hydrocarbon. For example, a hydrocarbon burns in excess oxygen to give 88 grams of carbon dioxide and 72 grams of water. What is the empirical formula? Well, of course, I am going to have to go from mass into moles. But first off, all of the carbon would become CO2. Relative molecular mass, 44. All of the hydrogen will become H2O. Relative molecular mass, 18. Dividing by the mass that I have, 88 grams for the carbon, by the relative molecular mass gives me the number of moles of CO2 produced. Same for my 72 grams of water. Divided through by the relative molecular mass gives me 4. And my simplest ratio of carbon in carbon dioxide to hydrogen in water. I'm saying 1 to 2, but if you look at it, I've highlighted carbon to show there's 1 carbon in CO2, 2 hydrogens in H2O. Each mole of H2O contains 2 hydrogen atoms. My simplest ratio of carbon to hydrogen is 1 to 4. Empirical formula, CH4. We have to approximate in determining empirical formula. All chemical formulae have simple whole number ratios. Measurements are never 100% accurate. We have to approximate to give whole number ratios. The empirical formula of a compound is calculated to contain, and it gives me the number of moles of carbon, hydrogen, and oxygen. If I'm starting off with the actual number of moles, I would divide through by the smallest number to give me the simplest ratio. Smallest number here, 0.48. So my carbon, 1. Hydrogen, 2.02. Oxygen comes out 1.06. Simplifying, or if you like approximating, gives the empirical formula as CH2O. That's it. If you got something out of that, please hit the like button. Please subscribe to be notified for more videos coming out.